Hi everyone, so this is going to be my video for the final exam. The question says a rectangular circuit is moved at a constant velocity of 3 meters per second into, through, and then out of a uniform 125 T magnet or 1.25 T magnetic field as shown in figure E29.33. The magnetic field region is considerably wider than 50 centimeters. Find the magnitude and direction, clockwise or counterclockwise, of the current induced in the circuit as it is A, going into the magnetic field, B, totally within the magnetic field but still moving, and C, moving out of the field. And then D, sketch a graph of the current in this circuit as a function of time, including the preceding three cases. So we can kind of sort of like gauge what like this problem is about. So we can immediately know that there is a change in the magnetic flux, right? That's produced by the EMF, right? So we know that a flux through a single loop is going to be BA times cosine, right? So then the induced EMF is going to be E equal to D, and then I don't know what the sign is called, I forgot, but that is the sign that we learned, dt, right? So then the induced current is going to be I is equal to ER. Okay, so bearing that in mind for A, we can essentially just kind of like plug in from here. So we can go to L is equal to 75 centimeters, just because you see that right here on the figure, right? And then basically you're just converting this to meters. So all you have to do is multiply this by 10 times negative 2, and then you're going to get 0.75 meters, right? So now we have, since we know that E can also be equal to BVL, right? We can say that the induced current is going to be E over R, right? Like just like up here. So since we know E is equal to BVL and we know this equation right here, then basically we can just put BVL in lieu of E. So that's going to be 1.25 times 3 for the velocity, right? And then 1.25 for the magnetic field. And then we're going to put also the 0.75 meters that we just calculated over 12.5 ohms, which is going to be our R, right? And when we do that, we are going to be getting 0.225 A, okay? Now, let me just move my little bubble real quick up here. So for B, now for B, notice that it says, when it's totally within the magnetic field but still moving. So, since we know that the circuit is in the magnetic field and it's still moving because that's literally what B says, there's no magnetic flux. So, and if there's no magnetic flux, then obviously this equation is the I over ER is going to be 0 as well. So this is just 0. This is really just it's just a matter of knowing Lenz's law and all that stuff. So yeah, so this doesn't really require that much work. Now I'm going to go ahead and block off this section of the work so that we can go ahead and do C on the left over here. Now for C, we are going to be doing the same equation really as A, because it's essentially sort of the same thing. They're both, A and C are both like transitioning into the field, if that makes any sense, or transitioning out of the field. And so for that reason, it's the same as A, right? So let me find my cursor real quick. So we're going to put same as A because it is quite literally the exact same work. So we wouldn't really have to write it again. Okay, so knowing that, right, we can go ahead and boom, put D. So D is where the graph is. Actually, let me do D like over here where I have more space. Okay, so D, we are going to make a graph of the current as a function of time, and that sort of also goes into the same three cases. Now, something that I forgot to mention for A and C is that C, I believe, is counterclockwise, right? And A is clockwise. So the work is the same, and the A for both is going to be 0.225. But since C is leaving the field, it's counterclockwise, and since A is entering the field, it's clockwise, right? So that is going to be what's reflected in the graph, and you're going to see that now. Let me just find my cursor again. Oh, there it is. Okay, so we can just go like this. This is going to be a very rudimentary graph, but you can just put I and then T. So then really what we're looking at is this is A, right? So da 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 da. And then once it's within the magnetic field, once it's at B, right, then we're going to experience a super sharp drop, right? Because there's no magnetic flux, so there's no induced current. So the I is at 0 and the T is at 0, and we're going to be traveling along this until we exit the field, right? Once we're moving out of the field, since we're going counterclockwise, we're going to be down here, right? And essentially, these are both like, if you can kind of see, this is almost like a reflection of sorts. And so you see that. Now, bear in mind that these are both 0.225, but you can see that, like, obviously, like this. So C, right? Actually, let's label this. So C, A, and B, right? So A is in the positive and C is in the negative, but both A and C are 0.225. What this is really trying to illustrate is that this isn't so much like, oh, the value is positive, the value is negative. It's so much as this part, the part where A is at, is clockwise, and then the bottom part is counterclockwise, right? That's really what the poles are trying to illustrate. So essentially, when you look at this graph, equate the positive y-axis to clockwise, and then equate the negative y-axis to counterclockwise. Aside from that, that is really it for this problem. So kind of like how I mentioned earlier, obviously, the whole point of this problem is to illustrate how the direction of the induced current, you can kind of figure that out using Lenz's law. So that is about it for my video. I hope you enjoyed it. Thank you so much.